Welcome back to Explaining Everything, the channel where we dive into the stories and mysteries behind everyday things, and occasionally world-ending science. Today's question comes from one of our curious viewers, Atomic Banana 92. Great name, and thanks for the suggestion. Atomic Banana. You asked, what is the difference between nuclear fusion and fission? Ah yes, two words that sound like cousins at a science family reunion, but actually describe very different ways of doing extremely dangerous things to atoms. Both involve releasing mind-melting amounts of energy, both can be used in bombs or power plants, and both are way too intense for your kitchen microwave. Let's get into it. Right here on Explaining Everything. Imagine an atom is like a Lego Death Star. In nuclear fission, we basically throw a neutron at it like a tiny wrecking ball. The atom, usually uranium-235 or plutonium-239, gets overwhelmed, panics, and splits into smaller atoms. Boom, fission. But wait, there's more. When that split happens, it releases energy and more neutrons, which go flying off and crash into other atoms, causing them to split too. And so begins a chain reaction. Fission is basically the domino effect if every domino exploded and also had strong opinions about thermodynamics. This is how most nuclear power plants work today. Not because it's the nicest option, but because it's the one we figured out first, and humans are nothing if not committed to using old methods until they break something. Now, fusion is the exact opposite. Instead of splitting atoms, we smush them together. Think of it like forcing two toddlers to share a toy, except the toy is a hydrogen nucleus and the toddlers are about to turn into helium and burst into flames. Fusion takes two light atoms, usually isotopes of hydrogen like deuterium and tritium, and merges them into one heavier atom. In the process, a small amount of mass gets converted into a huge amount of energy, like this could power a city or vaporize it kind of energy. Fusion is the process that powers the sun. Yes, that giant flaming ball in the sky is basically a 5-billion-year-old hydrogen party that never stops fusing. Scientists have been trying to recreate fusion on Earth for decades. But so far, the sun is still winning. Turns out, maintaining the temperature of a star in a lab is tricky. Who knew? Let's talk power. Both fusion and fission release energy, but fusion is the heavyweight champ here. Fission is like lighting a firecracker in a shoebox. It's loud, dangerous, and effective. Fusion is more like setting off a firecracker inside a volcano made of jet fuel. Fusion packs way more energy per atom. In fact, the hydrogen bomb, yes, the terrifying one, is a fusion bomb that uses a fission bomb just to get hot enough to start. That's right, a nuclear weapon so powerful it needs another nuclear weapon as a starter pack. Terrifying, but efficient. Okay, here's where things get messy. Nuclear reactions don't just walk away clean. They leave behind atomic garbage. Fission produces a lot of radioactive waste. Think of it as the glitter of the nuclear world. It's dangerous, it sticks around for thousands of years, and it somehow ends up places it shouldn't be. Nuclear power plants have to store it very carefully. And no, you can't just chuck it into the ocean or bury it in your backyard. We checked. Fusion, on the other hand, is much cleaner. It still makes some radioactive byproducts, especially from neutron interactions with the reactor materials. But it doesn't create long-lived radioactive waste like fission does. So fusion is kind of like making cookies and only spilling a little flour, whereas fission is making cookies by blowing up the kitchen. Here's the kicker. Fission? Pretty doable. That's how we got the first nuclear reactors in the 1940s. Give a neutron a uranium atom and some alone time, and boom, chain reaction. Fusion? Hoo boy. Fusion is like trying to microwave a bag of popcorn using only lightning and pure hope. To make fusion happen, you have to reach temperatures of over 100 million degrees Celsius, hotter than the core of the sun. At that point, matter turns into plasma, and you need magnets to keep it from touching the walls. Massive, donut-shaped magnets. Science gets weird fast, and even if you get fusion to happen, you have to do it in a way that creates more energy than you put in. So far, we've made fusion reactions work, but they still take more energy than they produce. That's not ideal. That's just a very expensive firework. So, what's the difference between nuclear fusion and fission? Fission splits heavy atoms apart. It's easier, dirtier, and already in use. Fusion joins light atoms together. It's cleaner, more powerful, but still in science's maybe one-day folder. Both are ways of unlocking the immense power trapped in atoms. One involves blowing them apart like an overinflated balloon. The other involves smushing them together like high-pressure friendship. Fusion is the dream. Clean, efficient, and less likely to leave behind glowing barrels. But until we figure out how to build a mini-sun without melting the lab, fission is still the reigning champ. So next time someone asks you which nuclear process is which, just remember, fission splits, fusion sticks, and both are way too much power for a toaster. If this video helped you learn about the difference of two nuclear powerhouses, don't forget to like, subscribe, and maybe the best nuclear power was the friends we made along the way. Also, if you have suggestions for our next video, feel free to share them in the comments below. We'll be sure to give you an acknowledgement for your contribution. Thank you for tuning in, and join us next time here in the channel that answers all the why, what, who, where, and how questions you've always wondered about, here on Explaining Everything.